This week, we'll be taking a final look at the ideal gas equation, and I'll have you doing a last bit of practice using the formula PV equals nRT. Remember to make sure your volume is always in liters, your R value matches the pressure used, and your temperature is always in Kelvin. Let's take a final look at that R value. The R value you're going to be using must match the pressure given to you. Last week, we only used the R value that was associated with atmospheres, and it was rounded to simply 0.082. This week, we'll be using the entire thing of 0.08206. The other R value that you used was the one associated with kilopascals. That one was 8.314, unrounded. You are also going to use the R value associated with a torr, or a millimeter of mercury, because they're the same thing, and that one will be 62.36. Simply make sure your R value is matching the appropriate pressure unit given to you in the problem. We will finish this week on one last little formula. This one's actually pretty easy to work with overall. We're going to be taking a look at Dalton's law of partial pressure. This states that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if they are present alone. So in other words, the total pressure of anything, be it a container, an entire room, is simply the sum of each individual gas. That's it. It's an addition problem. Pressure total equals the pressure of gas 1 plus the pressure of gas 2, and so forth. There's nothing else to it. The only thing that you might be asked is maybe what is the pressure, for example, of gas 2? We don't know what it is, but you do know the total pressure of the container. So you have to solve for X. But beyond that, there isn't too much more difficult to work with partial pressure. The last bit we'll take a look at here are some concepts, and you're not going to be tested on these, but it's useful to know how gases behave. So let's take a look at two definitions and then one tiny little change to the gas law itself. One of the features of gases you should be familiar with is simply known as effusion. This is how a gas is able to escape its container when it doesn't look like there's really an opening. Remember, gas molecules are quite literally atoms or very small molecules in size. They're moving at insanely high speeds, randomly and chaotically throughout the entire thing. They're going to find any small little hole or crack that might be available in their container, and they'll gradually ease their way out. You see this when a balloon that has been inflated gradually deflates over time even though it's been closed, because they're finding holes in the latex or even the balloon knot itself. This is a little different than something else you might already be familiar with, something known as diffusion. This is the spread of a substance as it goes throughout an entire space or other medium. If someone were to inject another gas into a room, it would be strongest initially where it was injected or put in, and then gradually diffuse throughout the remainder of the room, filling up the entire room or container. Finally, we're going to have a brief discussion about how real gases behave. We've been studying ideal gases, and the law really only works at really high temperatures and also very low pressures. At those circumstances, the forces that of a molecule that might be attracted to one another really don't exist. But under normal conditions, realistic conditions, gases actually are attracted to each other, even a tiny bit. And this can impact how they behave with one another. We've simply ignored that up until this point. This is something we tend to discuss more in the junior and senior year in the diploma chemistry level, but we do need to recognize that gases really do behave a little bit differently than what you would expect. Does it impact all of our answers at our level? Not really. But at higher level, when dealing with small amounts of gases, you can actually see some pretty big impacts due to the fact that gases have non-idealistic behaviors. And this comes to the end of the gas unit. At this point, we're done. In the following week, we'll be taking a look at solutions and how water behaves with chemistry. Water itself is an important topic overall, and that'll be our final unit for the year.